Okay, so thanks everyone for coming. So today I'll talk about conformal field theory. So there will be a gentle introduction to this very universal tool to theoretical physics. So you want to see the reason I chose this topic is partly because, as I already said, it's a very universally applicable tool to many questions in theoretical physics that you might be interested in, especially that concerns strongly coupled phenomena. And another reason is that it also has received a lot of development in recent years. And lastly, it's because this is a kind of a central tool that I use in my research. Okay. And this talk will be broken down to 3 parts, roughly speaking. In the first part, I'll introduce to you what is CCPP, conformal field theory. In the second part of the talk, I'll try to convince you why CFTs are interesting theories to study, okay, for a broad range of questions. And in the last part of the talk, I'll tell you briefly how are some kind of contemporary methods that people have employed, have been using to solve CFTs. This is supposed to be an informal Brown Bag talk. Please interrupt me at any point if you have any questions. Okay? So I understand that not all of you have a background knowledge on quantum field theory. So I'll start with a brief introduction to quantum field theory. Okay. If I'm writing too small, let me know. Okay. So quantum field theory is a very powerful and universal language for describing physical systems, especially those with large degrees of freedom. This interesting example of such systems show up in various branches of theoretical physics. For example, in statistical mechanics, okay. For example, some kind of lattice system with many lattice sites. And it also shows up in condensed matter physics. Or, for example, you're interested in some low energy quantum phenomena of some quantum lattice systems. And of course, this also shows up in particle physics. Where particle collision at high energy is known to produce a rich zoo of other particles. And also in cosmology, where quantum field theory have been used to model inflation. And lastly, quantum field theory provides the backbone for string theory as a description of quantum gravity. If you have not studied quantum field theory before, you may be slightly confused when I put statistical mechanics together with the other stuff, because this one is classical, whereas the other are quantum. The sense by quantum field theory, we use quantum field to describe statistical mechanics. Strictly speaking, you should think about quantum field theory in Euclidean sense, in which case the quantum fluctuations are characterized by thermal fluctuations in this statistical mechanics. Okay. And conventionally, A quantum field theory described by a path integral. By a Feynman path integral. Just like how you can reformulate quantum mechanics as a one-dimensional path integral. In the case of quantum field theory, this will be general higher dimension. And the path integral generally takes the following form. So it's going to be, so there's some action, which is some integral of some Lagrangian density, and is a functional of some fields, which are the quantum fields, phi, denoted collectively by phi, and some coupling constant, which are denoted by lambda I. Okay? And the dynamics of the quantum field theory is just governed by some path integral, which is the infinite dimensional integral over all configuration of this quantum field phi, weighted by the exponential of this action. Okay.
Can you cover a little bit over what phi is?
I'll give you examples.
Okay.
Yes. So here it's just a concise description of what quantum field is in terms of some elementary building blocks, quantum fields and couplings, and I'll give you examples in 30 seconds. Okay. And the example of what this action is, consider the case you have a single. Okay, maybe this is too small. I can go to the other. A particular example of this action, let's consider a case of a single quantum field, an action, say, in four-dimensional spacetime of the form, let's say in two-dimensional spacetime of the form where this is the gradient of the quantum field in both the time and space direction and some potential terms. For example, of this whole. So this will be a action of this quantum field and two couplings that defines the 1+1 or two-dimensional quantum field theory. Okay, so this model you can connect.
A moment ago you said infinite dimensional. That looks two-dimensional.
Right. So so when I say infinite dimensional, I meant this integral is an infinite dimensional integral in the sense that you're integrating over all phi as a function of two variables in this case. So that's an infinite dimensional space. But the action itself is a two-dimensional integral in this particular case. It's a path integral in the sense that you
Got it. This is good. Thank you.
Yes. Good. No problem then. Thanks for your question. And just to answer Mike's question, so how do we kind of make sense of this concretely? You can connect this to the more familiar examples of quantum mechanical systems as follows. So imagine you have a chain of quantum harmonic oscillators. Suppose you have infinite number of them. Okay? And think about this direction as x. Okay? And you can write down an action which just which you can derive from Hamiltonian that describes the coupling between this harmonic oscillators by some potential term as well as the connecting term. Okay, so for example, suppose the mass of the solid oscillators are all the same and have the same Hooke constant K. Okay, you can write down the coupling. I suppose the variables for this quantum mechanical freedom is Q, we label by Q. Okay. Because this action has the opposite sign for the potential. And there's somewhere over there. Okay. Okay, so this just describes this simple quantum mechanical system. If you have a finite system, then this sum truncates. So this describes the force, the potential between this adjacent oscillators, and this is this can try looking at it. Okay. So this is if the sum truncates, that's a usual like a quantum mechanical system. The quantum field theory is useful to describe the case when you have an infinite number of such oscillators. Okay, and in that case, you can go from here to the quantum field description by making the following replacement. That is, this Qn will correspond to a quantum field at point xn in the x direction. Okay, and there's a time dependence that just carries over from Q. And then this difference between adjacent Qs will translate into the x derivative. Okay, and now you can see how you go from this to this. That is, this gradient squared is really the time derivative squared plus the x derivative squared. Okay, so after rescaling of your phi, you can go directly from this action to this action. For example, here is in the minus plus convention for the Lorentzian metric.
Sorry, is what you've done just taking that to some continuous limit, or is there something else?
So here I'm just taking the number of these guys to be infinite. That's right.
Okay.
Yes.
And in some physical sense, is there any like, I mean, maybe in more realistic systems, this makes more, this question will make more sense, but how do you know what the right way to translate your discrete system to a continuous system is?
That's a very good question. That's a very good question. So there may be different ways to take the continuum limit. That happens a lot when you hand me a lattice system. What the quantum field theory is useful is to describe some kind of large scale dynamics of this system. For example, it will be useful to describe some kind of phonon modes of this chain of oscillators. And those description of those degrees of freedom will not depend on precisely how you take the continuum limit.
I see.
Yeah.
Okay.
This kind of question also shows up quite often in condensed matter system, where you can consider lattice of different shapes. But it turns out that if you're interested in some long distance dynamics, that will not depend on particular way that you tessellate your space. Okay. Yeah. Okay. And once you understand this kind of translation between like a chain of oscillators and the quantum field theory action in the quantum field description, you can also introduce additional potential terms. Okay. And as you know, like in just quantum mechanics, if you introduce this potential term, it already creates a lot of problem in trying to diagonalize the Hamiltonian and so on. But all those terms are easily captured within the quantum field description just by modifying the potentials this way. And the general framework of quantum field theory is to deal with this interacting system rather than the case with without potential. Okay, so this is what quantum field theory is. So what are some basic observables in quantum field theory? In quantum field theory, the basic observables are what's known as the correlation functions. So you have a bunch of quantum fields, which you can choose to insert where they are in the space-time, the x1, x2, and so on. And this in general will be a function of the positions as well as the coupling constants in your quantum field theory. And this is defined by the same path integral I wrote over there. Just as what you would do in statistical ensemble, insert the quantum field inside the integrand. So far, everything is kind of just like doing integral, but the kind of the devil is hidden in here because this is like an infinite dimensional integral, and care must be taken to define this measure carefully. And to be honest, physicists don't really have a mathematically rigorous way to define this measure, but except in very special cases. But there are kind of methods to get around that and producing sensible answers. But I should say a mathematical understanding of this path integral is still lacking.
When you say sensible answers, you mean answers that make correct predictions?
Yes, finite
Or-
answers. Finite answers
are good.
that make sense. Finite answers. So that would have the potential to agree with the experiments, and they do agree with experiments.
Right.
Yes. So this has to do with all this regularization and normalization of quantitatively compute from this. Okay. And perhaps this is already mentioned. So to solve a QFT means to determine this observables. And this is a problem that's just.
So maybe you could relate the observable to Z. Like, is Z ever useful on its own, or you have?
Yes,
to
Z
use
is very
some
useful.
sources?
Right. So Z itself is very useful. For example, what you can do is so the Z is going to be, because you're only integrating over 5, Z is going to be a function of it's going to be a function of lambda, for example. So if you compute this Z as a function of lambda by taking derivative with respect to lambda, you will get a subset of this kind of observables.
But that's for specific coupling form.
That's right. So in particular, when you take a functional derivative with respect to lambda, what you will get are not local insertions of these operators, but the operator integrated over the whole space. I can give you another example, which is perhaps more physical. So in the context where you can recast a statistical mechanics model, say defined on some large lattice in terms of path integral, this will literally compute the free energy. So it'll give you exponential to the minus inverse temperature times the free energy. And if you can compute this, you will know precisely the free energy as a function of, for example, your magnetic field, or as a function of other background that you may have. All right. So I was just saying that to solve a QFT means to determine this kind of observables, and I should also say the kind of particle scattering amplitudes that we know how to compute in QFT 101. And which leads to precise predictions at FC can all be extracted from the correlation functions by doing a Fourier transform with respect to the coordinates, because these field operators are the ones that create particle states. In the case we have a good asymptotic S matrix. Okay. So all those information are contained in this correlator. But it turns out that this kind of ambition to solve a QFT this way is really beyond our reach at the moment. And we will even be satisfied with solving a subsector of these observables, or exploring a subset of phenomena that arise in a kind of a strongly coupled common field theory. For example, maybe perhaps we can explain if it's, we don't really know how to do it, but we'll hope to try to kind of derive, say, the confinement in Yamil's theory, and prove the mass gap or compute the mass gap from the description in the ultraviolet given by the Yamil's theory. But even this kind of a subset of this problem is already difficult. That's what I try to emphasize. But there are some substantial progress, which is made in computing these correlators for derivative in couplings. Okay? This follows from the Feynman rules. So here, by phi really mean, broadly speaking, the collection of quantum fields in your quantum field theory. So it could include, for example, the quark fields and the gluon fields in the standard model. And we know in standard model that we can extract very accurate predictions by doing this kind of computation using Feynman diagrams, which we've heard from previous Brown Bag talk. And they give rise to very amazing agreements with experiments observed at HC. Okay? So obvious pro point is that this gives you accurate predictions for standard model and experiments as example. Okay, but there's also a very a disadvantage to this perturbative approach. That is, we don't really have any kind of understanding of these objects as a function of lambda. For example, at finite lambda, so we understand using finite rules how this function behaves at small lambda in the expansion in lambda, which is actually not convergent. Okay, that's for another occasion. And we, for the similar reason, we don't really have any idea what this function is at a finite lambda. But the finite lambda dependence of this function is important. For example, the interesting phase transitions in this quantum field theory will happen at finite lambda. So in order to understand these phase transitions, we need to understand these functions at finite lambda. And here I just want to emphasize that this perturbative approach will be obviously lacking in the sense of not giving up non-perturbative understanding. And for example, phase transitions. And we'll see this question will be addressed in a number of cases by conformal field theory. All right. What is the conformal field theory? So after I have introduced to you about what the QFT is, it's very easy to define what the conformal field theory is. So these are just quantum field theories with a special set of symmetries known as conformal symmetry. So what are conformal symmetries? So here, for simplicity, I'll restrict to the quantum field theories that the energy theorists are mostly interested in, which are quantum field theory that preserves a space-time symmetry known as the Poincare group. Okay, so the quantum field theory of interest in will be invariant on this group. This group contains, so suppose we're considering a d-dimensional quantum field theory. So the example I give was just now was the case d equal to 2. So the d-dimensional quantum field theory has a Poincare group that includes a translation in space-time, which generates this trivial subgroup. And there's also the rotation group, or more precisely the Lorentz group in the corresponding space-time dimension, SO d minus 1, 1. Okay. And this, as you have learned in classical mechanics, whenever you have a symmetry, there's another current. Okay. And in the case of the Poincare symmetry, the another current is given by an object with two indices in the space-time, where this mu and nu represent the space-time indices. In this case, in our space-time will be only from 0 to 0, 1, 2, 3. In the general d-dimensional, run from 0, 1, all the way to d minus 1. And the stress tensor, which is another current for the symmetry, has two indices, mu and nu. They satisfy a number of properties, which come from the so-called Noether theorem, and in the quantum theory correspond to the so-called word indices. It says that this stress tensor operator is symmetric. Okay. So in the concrete quantum field theory, the stress tensor will be some field out of combinations of this quantum field and their derivatives, so that they have the right transformation properties, which I'll write here. And also it satisfies the conservation law, which says the divergence of this two index operator is 0 independent of the choice of one of the index. Okay. So this is the kind of the cherished operator for any local quantum field theory, the stress tensor. And to go from a quantum field theory to a conformal field theory, you just have need to require scale invariance. Okay? So if you demand on top of the Poincare invariance, a scale invariance, meaning that you demand the theory to be invariant under rescaling. So rescaling this coordinates to by a constant lambda, that's a real number. Okay. Up to some caveat, this will imply an additional word identity, just run by running the same theorem. Another procedure, you find that the additional word identity says that this symmetric, so-called symmetric rank 2 tensor is also traceless. Okay? So here I'm using the Einstein convention where the index are summed over. And this, it turns out that this condition implies in unitary quantum field theories that the theory is a conformal invariant. Okay, so there's an enlarged symmetry group, the conformal group. Under which the theory is invariant.
Can I just,
Yes.
so since I care about this details, is this SOD D-1,
Yeah.
Why did you not write O D-1?
So very good question. So for the discussion I'm having here, just for simplicity, I'm dropping all the discrete.
Because the
discrete
Noether
symmetry.
current only comes from like the differentiable symmetry.
That's right.
So
So
the reflections don't enter into this
that's right.
argument at all.
That's right. That's right. Essentially, because the Noether currents only care about the Lie algebra of the underlying symmetry group, and for the Lie algebra, only the local structure is relevant. And this global structure that you mentioned is very important, but it's not important for this discussion, right?
Good, excellent. And then how does that scale invariance? I would have thought SOD comma 2 would be like a rotation with 2 time coordinates.
That's right. So you can think about it this way.
But
So-
what does that have to do with scale invariance? Is that something you're going to talk about, or is that obvious to people
So-
in the room? 'Cause
right,
it's
so-
not obvious to me.
So I will talk. I was just going to talk about it more,
Okay,
but maybe just to answer your question. So there are various ways to think about this. If you think about it as the following, containing the following maximal subgroup, when you split the D, 2 into D-1, 1, and 1, 1. Okay, if you splitting this way, this is precisely the Lorentz group, and this is the dilatation symmetry. Sorry, this scaling symmetry, which is also known as the dilatation symmetry I was talking about. They commute. Okay.
I almost believe that.
But-
Good.
and
Fine,
I'll-
you've given me a homework problem.
But it's not a trivial
It's
statement.
not
So
obvious.
it's
I
a
think.
it's highly so I made a leap here. There's a very non-trivial statement going on here. The Poincare symmetry together with scale invariance, just at the group theory level, does not generate SOD, 2. So this and this are subgroup of SOD, 2, and they do not generate SOD, 2 together.
Fine.
The non-trivial statement is that when the stress tensor is trivial, it leads to enhanced symmetry that include these guys and enhanced all the way to this
I see.
guy. And this other element, which I didn't talk about, is known as the special conformal transformation. It's a little weird. The way it acts, let me just write it here. The way it acts is known as the special conformal transformation. The way it acts is that it sends this coordinate to a following. So by x squared, I mean, so this is the usual high energy notation. By x squared, I really mean it's the Einstein convention is when x and contracted together, minus 1 plus b dot x plus x squared. Okay, and here b is a constant vector. Okay, so these are a set of group elements labeled by a vector in your space-time. just like the translation subgroup of the point group. Okay. These guys are part of the SOD-2, but it's not generated by just the limitation and the point group.
Good.
It's some enhanced symmetry you get because the stress tensor is stressless.
Okay, so let me ask one more question and then I will rest, which is you said that the scale invariance through the Noether procedure
Yeah.
leads that T mu mu is 0.
Yes, up
Then
to
you
some
said-
extent, which I
Then
believe.
you said T mu mu is 0 actually is enforced by some, or like gives you some additional
That's right.
freedoms.
That's right. That's right.
So is that because there's some additional physics content that does it, or is it because the Noether argument somehow realizes or exposes other freedoms?
Well, it just
That like if you have this freedom, you also implicitly always have this additional freedom.
it's partially because this object it's come with two indices, so it's not just the current. So you have the freedom to contract the other index. Yeah. So there are multiple currents to construct just from a single operator. So for example, for dilatation, the current. So for rotation, for dilatation, the current, the Noether current you construct is x mu x mu contract with T mu mu. Okay. Right. And this is conserved. So Noether procedure will tell you get the conserved current associated with symmetry. And this is conserved because if the derivative hits this guy, it will conserve because of this. And if the derivative hits this guy, it will give you the trace. And the claim is that for this symmetries, you can also write down current of this form, where the x dependence is more complicated, it's actually quadratic. But it's chosen in a way such that you have this additional currents.
Okay. Yeah. That doesn't answer my question, but that's adjacent enough that I think we should continue.
Yeah.
But you also mentioned unitarity.
Yes. So
But
very good.
Many of these motivating examples don't really require unitarity to be interesting.
That's right. So here, in the more general case where you don't have unitarity, then you just insist on the CFP being SOD, 2 invariant. You don't have to go through this procedure. That
Okay. Yeah, I mean, just because in statistical mechanics, you might
That's
have
right.
a system which you know is point gray invariant and you know is scale invariant,
yes,
but there's no particular reason to expect it to be unitary.
that's right. That's right. That's right. So in those theories, the theory is just defined as a quantum field theory with conformal symmetry. And it has a bunch of stress tensors. Sorry, it has this stress tensor with this property, but it's no longer true that in general non-unitary quantum field theories, point gray invariance plus scale invariance would imply conformal invariance. That logic doesn't hold anymore, but you can still define the CFP as a theory with this cherished word. Okay. So how much time is that?
So about 20 minutes.
20 minutes.
Yeah.
Okay. I think I can do it. So I've explained what is CFP. Now let's get to why is CFP an interesting thing to study. Okay. So here I will not go through details, but I'll give you a bunch of examples which can be solved using CFP. Okay? And then I'll try to motivate that it's an important question that is to solve the CFPs. And then I'll describe some methods that one can use to solve them. Okay. So the examples that I want to tell you for which the CFPs play an important role are the following. Okay. So first of all, as already mentioned, the CFPs are good descriptions at second order phase transitions. I'll give an explicit example of what I mean. Okay. Quickly, for each of these points that I'm going to lay out here, which is also equivalent to description of critical points. The CFPs are also important for describing renormalization. So in quantum field theory, this important idea that is due to Wilson, that is the renormalization group flow. And the CFPs are useful for describing fixed points of the renormalization group flow. And I should say it's not exaggerating. It is because this RG picture that the physicists are really become kind of reconciled themselves with all the kind of infinities that you see in the computation involving Feynman diagrams. So this is really conceptual, an important conceptual breakthrough in the development of conformal field theory, and conformal field theory describes the fixed points of the homologous group flows. And lastly, more recently, thanks to the so-called ADS-CFT correspondence, there's a precise relation between reasonably defined CFT, satisfy a bunch of quantifiers which are not explained here. For any CFT with those properties, there's a conjecture that there's a holographic dual, which is a quantum gravity theory in one higher dimension. And this has provided a way to kind of at least gain some qualitative understanding for various questions you want to ask in quantum gravity, such as black hole information problem and evaporation of black hole and so on. Okay. So let me give you some concrete examples. I'll leave out this. This will be another lecture. I'll give you some concrete examples of what I'm talking about here. Okay. So let's start with phase transitions in classical stat-max systems. Okay. And what's more simpler than a magnet? Okay, so let's start with example 1. Okay. So let's consider a magnet. And we can, so the thing about magnet is that if it there's a magnetization, which I denote by n vector, which describes the alignment of this things when you apply transverse magnetic field, which I denote by H. Okay. And in the study of magnets, suppose you measure. Okay, so there's this famous phase diagram. So you have H and temperature. Suppose you measure the magnetization of the magnet as a function of temperature at 0 magnetic field, transverse magnetic field. There's this famous region called the paramagnetic phase, which is the reason that we have magnets at room temperature that you can use to put stuff on your fridge. Okay. So these are this is the phase where the magnet still has is still magnetic, even though the transverse magnetic field is turned off. But as it turns out, if you heat up the magnet, still has 0 magnetic field at a certain critical temperature, the magnet will transform would go into a different phase known as sorry. This is a ferromagnetic phase. We're going to the paramagnetic phase, where the spins will stop being aligned and it's chaotic, and you lose magnetization. Okay, and the claim is that this the physics near this transition point is described by a CFT. Okay? I'll tell you momentarily what the CFT is. Example number 2. Okay. At the same level of familiarity, boiling water. Okay. So we all know the phase diagram of water as a function of pressure and temperature. Okay. It roughly goes like this. Okay. I'm using the Kelvin units. Okay, so this is a 0. Okay, and this is in the say in the atmosphere temperature. Sorry, pressure. And so this is the phase when it's in the ice phase. This is the liquid phase, and this is the vapor phase. Okay. And once again, as you heat up the water to a certain stage at this critical temperature, this first order transition line stops. And this is roughly about 647 Kelvin. Okay, so this is not some experiment you can do at home, but you have to trust me on this. Okay. And 300, roughly 400 times the atmosphere pressure. Once again, the first order transition line stops, just like here. And you get a critical phase. And this is again described by a CFP.
I like that in both of these examples, you don't tell us what happens to the right of the transition.
Oh, so here on the right of transition, it's just going to be some paramagnet phase, and you lose mechanization.
You basically can't magnetize the thing.
Yeah.
And then here, somehow past this,
Some
there's no
super-
difference between the water and the vapor. They
It's
just
some
become
kind of
indistinguishable.
supercritical. It's yeah, you cannot distinguish between water and vapor beyond this temperature.
Only distinguish them by going through the boundary.
Yeah, but then but then you can go around, you can continuously go from vapor to water without
Yeah,
a change.
Yeah, that's right. There's a balance between the kind of interchange between these two phases. Exactly.
We astronomers, by the way, care about the triple point way more than the critical point. The triple point, that is, there's a lot of work on that.
I see. So this kind of the stat mag models can typically be incorporated into the context of quantum field theory using this mean field theory approach. I don't remember on top of my head if there's understanding of the triple point from the mean field theory approach, but if that's the case, then essentially it can also be applied to astronomical situations. Right? So I should say that even like weather can be formulated as quantum field theory, and there's some kind of fluctuations, and I think it's not clear, completely known how to take into account those fluctuations. So a third example is a back of envelope example. It's a stat mag model, sometimes known as the icing model. Let me focus on the case when the underlying lattice of this icing model is a three-dimensional square lattice. This has generalization to other cases. So in this case, this is probably related to what Yassin asked about. In this case, the Partition function has a very concrete expression in terms of the degrees freedom on each lattice site. And it's a sum over the individual spins at each site, weighted by the Boltzmann factor, where this is where this you're supposed to sum over the nearest neighbor pairs. Okay, so this is just the icing model, and this is the particular discretization of the three-dimensional of the top integral for a specific theory, which I'll write down momentarily. Yes, that's known as some kind of Mengel-Ginsburg field theory.
Your infinite dimensional integral became a sum over
That's
all
right.
possible states.
That's right, exactly. So the top integral will be equivalent in this language to summing over all configuration of spins over this three-dimensional infinite size lattice. Okay. And here, the CFE arises when you tune this J over T to some critical value. Where once again, this model exhibits critical phenomena in the sense that, for example, the correlation function. So first of all, the free energy will have some behavior that mimic the critical behavior as in these systems, as well as the correlation functions of the individual spins would have some behavior that hints at a kind of a scaling behavior. For example, the correlation function of the spins would fall off algebraically as a function of the separation between individual sites.
Tune J over T and take a continuum limit.
Sorry?
You take a continuum limit as well as tuning J over T.
That's right. Yeah, I think I'm putting a lot of caveats under that. Thanks for the clarification. And as we're just saying, there's a precise quantum field theory which describes the continuum limit of this. This quantum field theory for general couplings. This quantum field theory has the action which we have already written down before. But in this case, it's a three-dimensional theory. So the action is a three-dimensional integral that involves the so-called connected term for a single scalar field phi, and the mass term and the potential term. Okay. And once again, this theory under RG flow, which I will not go into detail, unfortunately, in this talk, will again flow to a CFT, which means that for observable in this quantum field theory, that describe correlation functions of this quantum field, if you consider the large distance limit when the points are separated far enough from each other, that correlator is well approximated by the corresponding correlator in the CFT. Now, the amazing thing is that I've given you a bunch of examples, right? So they look very different. Apart from these two, which I already told you they're related. These are very different systems, but these CFTs, okay, all these CFTs are described by the same CFT.
Sorry, this is a very naive question, but maybe from my background, I mean, I know a CFT, I can calculate OPs, correlators, how to transform, but I'm always confused. Like I have a magnet,
Yes.
but I always saw these pictures. Like, what's the really conformal thing, or the scale invariant, or the inverse distance property of a magnet or water? I mean, how these are clearly seen as a CFT? Because for me, a CFT is I calculate correlators.
Yes. So CFT, so for the experts in the audience, CFT is just about critical exponents and the correlation functions, OP coefficients. These words I'll explain what they mean, but just for the people who are familiar with this jargon, all those information are captured and measurable at the critical point by studying how the thermodynamic observables scale as you zoom onto the critical point. For example, if you consider the dimensionless temperature, okay, the critical exponent of the CFT is understood by seeing how, for example, in this case, how the mechanization scales with temperature for this dimensionless temperature. There's some non-trivial scaling behavior. The exponent keep track of the critical exponent.
I see, like if the system gets massless, then the two-point function decays.
That's right, algebraically.
But then it's like, it means if they have a longer bar, it behaves as a smaller bar. My problem is with the intuition, besides with the math. I mean, what is the scale invariant in a magnet or in a, have a bucket of water? That's always my problem.
So the
I have
scaling
with
behavior is about certain collective excitations near the phase transition. It's not saying the magnet is scaling invariant. It's about the magnet. It's about the fluctuations of the state near the critical point. Those states have the scale invariance property. So if you like, it's about scale invariance of like some kind of quasi particles near the critical point. It's not the scale invariance of this spinning.
Can we think of it as like, if you have a power spectrum, it becomes scale invariant around this transition points? Like you have the same power at each wavelength independently of scale. Is that a good way to think about it?
Can you say it again?
Like, I don't know, if you look at the water going from vapor to water.
Yes.
You see, when you do, as an undergrad, you see this experiment, it goes fuzzy, I don't know what goes on, but there's presumably some kind of turbulent stuff going on. Perhaps you could measure the power spectrum or, I don't know, the density or.
Yeah, presumably, yes, but I'm not so sure about, so what I can say concretely here, for example, you can see how the specific heat scales with this dimensionless temperature as you goes to the critical point. The specific heat will diverge at this point. You can see precisely how it diverges as t goes to 0. And that scaling behavior is controlled by the CFT.
If there's turbulence, the first order
No,
I think it's a joint question, like just some.
I suppose the classical
Yeah,
example
Yes, exactly.
from the 1913 was critical opalescence.
That's right. So this is closely related to the
Yeah.
We
So
have
there
to
is
find-
really the fluctuations in the density of the
That's right.
gas.
That's right. That's
And
right.
that scales.
That's right.
That
That's
doesn't have any scaling. It scales
That's
with
right.
the power.
So that is really, so that's thanks to a very good example. So that case is really visible. Okay. So you can see that in that case, I think there's some experiments that you can see with your eye that the phase become critical.
So which case I missed?
The critical opalescence.
Yeah.
Oh, okay, so it is this power, the scale invariant power spectrum.
Yeah, so this is the power spectrum in the density of the gas at the critical
That's right.
point. So if you scatter light, you can see that it opalesces. I think that's-
But it's probably not for water, strictly speaking, for another liquid. This will be.
Yeah.
Yeah.
At the beginning, you gave this nice argument that quantum field theory describes this, big range of different
Yes, yes.
systems in nature. And then in example 4, you say that QFT flows to a CFT generically under
Yes.
a G flow. On the other hand, in the first 3 examples, one had to tune something very precisely to get to a CFT.
Right.
So isn't there some tension? Or are you saying only in the Poincare invariant case?
So, so let me say the following. So, even for this quantum field theory, you have to tune something because there are so even though it can flow to CFT, but the choice of the IR CFT could be different. So, for example, for this particular case, so depending on how much the mass is and what's the sign of this mass square, you can either flow to a symmetry breaking phase, or you can flow to the CFT phase. And in more kind of contrived examples, there are multiple IR fixed points that's admissible. But even in this case, which I didn't explain, the symmetry here is playing an important role. For example, the reason that this is like a one-dimensional diagram is because there's a manifest Z2 symmetry. And if you insist on the Z2 symmetry, there's only one parameter in Z2. And that's the temperature because the magnetic field is Z2 odd. But in this picture, the Z2 symmetry is not manifest, so there are 2 parameters in Z2, like pressure and temperature. So here, the implicit thing about this model is that this model is Z2 symmetric. So it's kind of more like this rather than the water. I'm not totally sure if that addresses your question.
Well, I mean, the question is just, if quantum field theory is really so general, it can really describe all these things, it should describe all 4 of these examples.
Yeah.
So that means that in the first 3, it's not true that the quantum field that describes them flows to a CFT in any simple sense, right? Unless you tune it.
Right.
And so there's a little bit more to the story than, and I mean, it's partly because in these first 2 examples, there's no Poincare invariance.
That's right. That's right. So quantum field theory will be useful in the first 3 examples to describe the physics in the vicinity of this phase transition. But because there's no kind of UV description, which is manifestly Poincare invariant, because as you said, we have less control on our RG flows, for example. You can still talk about RG flows in general statistical models without relying on any kind of any kind of relativistic invariance. But yeah, it's less control.
So I have a dumb question based on that.
Go ahead.
Question, which is it a statement? Is that statement you just made about the descriptions around the critical point? Is that a statement you can make around any point? It's just that it would be a different theory, or is there something special about a critical point that for some reason it has these symmetries?
That's right. So I can only say confidently around critical points. First StatMech model. So depending on the context, if we're talking about quantum field theory, of course it's, like SNAR model. How to describe it. Yes. But if you throw me a random StatMech model or throw me a random condensed matter system, the quantum field theory, I only believe the quantum field theory will be useful around the phase transition.
Okay.
Yeah. But they're having attempts to
no other points.
Well, so I don't want to say that for sure because our understanding of quantum field theory is pretty incomplete, and there are various generalizations of quantum field theory where you kind of you abandon some nice symmetries. For example, if you abandon Lorentz symmetry but just insist on rotated symmetry and something like what's known as Gaussian symmetry, and there's a larger class of quantum field theory that people have studied. And more recently, there are even more exotic quantum field theories that describe like fractal models, which do not have any remnants of the the Poincare symmetry, really, just rotation symmetry.
Okay.
Yeah.
But you say you use this word algebraic. There's these algebraic dependencies, and that has something to do with scale freeness, right? Because it is.
That's right. So I should have emphasized.
So really, what's happening is that as you get close to the critical point, certain dependencies have an algebraic form that means that you can see them in a scale-free way.
That's right. That's right. So that's very robust, and that's something you can. Yes, that's right. But you can kind of put back in the scale dependence by what's known as considering deformations of your CFD. So the CFT could have various operators, right? And you can use those operators to define
Which
a
are like
theory.
perturbations.
And
on it.
that's right, exactly.
Got it. So you could imagine then expanding to some finite region around those.
That's right, exactly. But they extrapolate that description far away from the phase transition where the QFT is useful. That is still an open question.
Got it.
Okay, so the kind of lesson I want to emphasize here is just that the CFT has this following key feature that is universal. Okay, and because it has this extra symmetry, which I mentioned in the earlier section, the conformal symmetry, and one can hope whether this gives rise to some kind of novel way to solve the quantum field theory in the CFT in this case that is beyond the usual Feynman rules. Okay, that can tell us about the observables directly at this strong coupling point from some Lagrangian description.
So we are reaching the end. I know
Okay.
the interruption.
Okay. I think it was, I think the discussion was nice. Let me just say without writing anything, summarize like in 3 minutes. Okay.
Yeah.
Right. So the idea to solve. Okay, let me just write on one word. Okay. So the strategy,
As long as it's not a German word. That's needed.
So the general strategy to solve the CFTs that is beyond the perturbation theory approach to generic quantum field theory is known as the bootstrap. I think it's something that Mike asked me a few weeks ago during introduction I was giving, and I didn't explain it well. So I don't have time to explain it here either, but you can ask me afterwards. But let me just say that the principle here is that you want to explore the symmetries. So you have this enhanced SOD(2) here. And this is going to give you a lot of constraint on these correlation functions. Okay. And just by kind of studying these constraints with minimal input, you can actually determine these correlation functions. For example, in the case of this examples that I described over there, there's a exclusion plot you can derive by running this bootstrap program, just exploring constraint of symmetry. And the theory has two parameters. Let me just call it x and y. So secretly speaking, these are parameters that label the critical exponent. So as I already mentioned, from these diagrams here, you see that there are two relevant operators. In this case, you don't see the other one because you insist on this symmetry, but from water, you clearly see there are two parameters you need to tune to reach the critical point. So the the exclusion plot I'm plotting here as a function of the critical exponents of the two relevant parameters. Okay. And the exclusion plot looks like following. Okay. Just by consistency of the symmetry, it tells you that everything outside of this kind of shape is excluded. Meaning that whatever the CFE is that describe all these cases must have critical exponents that lie in this region. Okay. And the refined analysis of the bootstrap tells you that the CFE sits precisely at this kink with precise value of x and y. Okay. That is more precise than ever obtained using any other methods. Okay. Sorry? So x and y are related to the critical exponents at this point. Okay. In the CFT language, these are the operators of the two relevant operators, meaning in this case operators with dimensions smaller than 3, and their dimensions are determined. They're determined x and y essentially.
I don't think so. For examples is one of the same example. I think it would be useful.
Sorry.
I don't think you explicitly said that this, for examples, is one.
Oh, I said.
Did you say?
Yeah. Okay. That's the important thing. If I didn't say that, I should say that now. The magic of the CFT is that very different systems are described by the same universality class. In this case, by this Ising CFT, which sits here. And the bootstrap gives the most accurate theoretical prediction for the critical exponents. And this, I'm just giving you one example out of like hundreds of examples. There's also the example that concerns the critical phase of the thin layer of superfluid. In that case, it's a quantum critical phenomenon. And that critical point is described by so-called O2 CFT, which is generalization of a CFT. Generalization of a CFT described by this quantum field theory in the UV. We introduce extra scalar fields, 2 of them. Yeah, I think with that I'll end. And if there are any questions, I'm happy to discuss further.
Any more questions?
Yes.
So I had a few questions about kind of the, I guess, criteria for a CFT.
Yeah.
So you showed that you need to have this traceless energy momentum tensor,
Yes.
right? And you said that that follows from dilatation symmetry.
Yes.
But so when we construct stress energy or energy momentum tensor in QFT, right,
Yes.
there are many ways to do it.
That's right.
So sometimes we have, like, we can do the Einstein-Hilbert action and vary over the metric, or we can do the canonical way. And so sometimes we add this.
You're talking about gravity. There's no Einstein-Hilbert action here, but you can. Maybe what you meant is that one way to derive the stress tensor is by coupling your theory to gravity.
Yes.
Write down the diffeomorphism form of this coupling, and then take a functional derivative with respect to the background metric.
That's it.
And this way you can get a stress tensor, which maybe you want to say is that they give you a stress tensor with a derived property that is already symmetric on the nodes, and for a CFT will be traceless.
And so sometimes you have this freedom, right? Because you're integrating out the Lagrangian.
That's right. So that's
sometimes-
a very good question. So in general, operators in quantum field theory and in CFT, they can be ambiguous up to some redefinitions. So here but for this CFT, these ambiguities are fixed by demanding it to be symmetric and traceless. So the ambiguities are give rise to some kind of total or some derivatives which do not modify the charge that generates the symmetry, but modify the current itself. But this, maybe that's what you have in mind.
Yeah. So is it? Are you saying that we can always kind of construct a traceless energy momentum tensor? So if we can't construct that, that's when we don't have it.
That's right. That's right. If you cannot construct it,
Okay.
at least it will not give you a conventional CFT.
Okay. And then I had another question too. So does the converse hold? So if you have a traceless energy momentum tensor,
Yes.
does that mean that your theory obeys dilatation
Yes.
symmetry?
Yes.
Okay. And
If it's already conserved, so divergence is 0, and it's traceless, then it will have dilatation symmetry, just as what I mentioned.
And then I had a last question that I was a bit confused on. So there's this conformal symmetry and
Yeah.
then there's dilatation symmetry, and they're not quite the same.
So
And I didn't quite
yeah, so this is
understand.
related to something that David asked. So the
Yeah.
conformal group contains this maximal subgroup. And this is the part that generates the dilatation symmetry. And this is the part that generates the Lorentz rotation. Okay. For example, the SOD model, but this one subgroup is the one generates rotation at fixed time.
Right.
And this is the generate, and it contains also the boosters. So
Okay.
this is the-
Okay, I got it.
So these things are packed together into this bigger conformal group, which contains in addition elements like the special conformal transformation, which is more strange.
Great. Thank you.
You didn't have the time to talk about the DSCFT.
Yeah, that will be a whole, I think there will be like
Out
another
of scope.
set of discussions, yeah. I think even, yeah, so,
Massimo's doing that next week, right?
right. Yeah, and I also didn't get to the part about representation theory, which I thought maybe would be interesting to, for example, to David, because they talked about something similar. There's a beautiful representation theory associated with this group. So a part of this CFT, a part of the recent development in CFT is trying to understand this representation theory as good as you can. The representation theory is what we will call the kinematic part of the problem to try to solve the CFT. And there's the dynamical part, which is what I was talking about here. But the strategy is kind of try to understand the kinematic part as well as we can to kind of speed up this kind of potential constraint from on the dynamical part of the CFT data. And I should say the reference theory is not completely understood, but lots of progress has been made.
So let's thank Yifan again, but you can continue discussing afterwards. stop the discussion, but I do want to give people a chance to go. Thank you. I'm going to stop there.
Thanks.